Je pense que je parlais combien de temps depuis que j'ai ce outil. Je vais être genre non.
Okay, let us continue. So before the break, we looked at gradient descent, right? Like so, which is basically an iterative algorithm to find minimum of a function, right? So the advantage of gradient descent when compared to the closed form solution is sometimes the closed form solution is just not possible to compute, or it is too costly to compute, right? So then you could go for gradient descent based approach, which is cheaper. In the sense, computing gradients is easy. And once you compute the gradient, like you just do this iteratively and you do this until convergence, right? So gradient descent is probably one of the most popular machine learning algorithms like that exist right now. Okay, almost all successful ML algorithms right now use gradient descent for learning the parameters. Okay, which means there's a lot of work in improving gradient descent, right? Like so, like making it faster, making it better, and all those things, right? Like so, we're going to talk about few variants of gradient descent today, but we will have a full-fledged lecture on optimization, like in the second half of the course, like where we will revisit gradient descent and look at more variants further. Okay, so for today, what we are going to do is we'll start with the full batch version, which is what we discussed before the break. Okay, so what is a full batch gradient descent? So full batch gradient descent means I'm using all the examples in the training set to compute the gradient. Okay, so if you think about it, that is what we were doing here, right? Like when I computed the gradient, I'm actually computing the gradient for the error function for all the n examples, right? In some sense, this is the true gradient because the function I want to minimize is actually sum of errors for all the examples, right? I'm not just interested in minimizing some of the, like the loss for some of the examples. I'm actually interested in minimizing the loss for all the examples in the training set, which means the true function I care about is the summation over n, the error for individual examples. And the true gradient is actually gradient for this complete loss function, right? So that is what we're going to call as full batch gradient descent. So in full batch gradient descent, typically the loss, let's say something like summation or n loss n, which just means that there's individual loss function for each example. I'm summing it for n times, right? Now the gradient is given by dou by dou w of summation over n loss here. And wj is equal to wj minus alpha times the gradient. Is that clear? Yeah. Yes, for each parameter, some parameter wj. Okay. So now sometimes people do an extreme version of this algorithm, like where instead of going through all the examples, doing the summation for the gradient, right? Just compute the loss for one example, compute the gradient with respect to that example, apply this gradient and move on. Okay, so that is called stochastic gradient descent. The stochastic gradient descent works like this. So basically the loss, I'm going to pick a random loss. Let's just say loss at k, where k belongs to 1 to n. Okay, now the stochastic gradient is given as dou by dou w of loss at k and Wj is equal to Wj minus alpha times the stochastic gradient. This is SJD. Okay. First of all, would the stochastic gradient exactly match the true gradient? Is it? So it's an approximation, right? It's a noisy approximation. So stochastic gradient that you see here, right, is actually a noisy approximation of the true gradient G. Okay. However, sometimes it's more useful. Let's look at some examples. For example, let's say I have million data points. Okay. I have million data points. I'm doing gradient descent. Now, to take every step in the gradient descent, I need to go through all the million data points, compute the gradient, sum them, then you do one step. Right? This is a very costly process. Like every step of gradient descent requires million computations. Now, it might be the case that there's a lot of overlap between these data points. I don't need to see all the million. It might also be the case that I'm too far from the minima, so I can just take an approximate step. I don't need the exact step, right? So for all these reasons, it makes sense to just look at one example and see where the example is sending me, right? Like, so take a step and repeat this for all the examples in the batch, right? So that is stochastic gradient descent. Like stochastic gradient descent would actually take million steps before full gradient descent takes one step for million examples, right? It's actually moving for every example, like not just wait for the whole data set to be completed and then take a step. Question? That's a good question. Let's think through that, right? Like, so the question is, if I do stochastic gradient descent and go through the full data, is it equivalent to doing full batch gradient descent? Is it exactly equivalent? That's your question, right? Is it exactly equivalent? Think about it. Think about the steps. Like, so can you repeat your question?
And go through all the data, aren't we going to have the result of gradient descent and optimize the result?
What is optimized result? The minimum. Okay. So, okay. There are many variants for this question. The kind of question that you are asking, answer might be yes. So the question, to be clear, the question is, if I follow full gradient descent and reach a minimum, and I follow stochastic gradient descent and I reach a minimum, is it going to be the same minimum? Is that a right way to put your question? So what do you think? Yeah.
I think that at the end it's going to be the same result. What is changed is the time of training.
In the end, it is going to be the same, but what changes is the time of training. Answer is a bit more complicated than that. In the end, it is going to be same if you have a convex function. Okay. It need not be same when you have non-convex function. So have some thoughts?
Before it stops, you would stop when the gradient equals 0.
That's a good question. So, well, Do you agree that when you reach the minimum, eventually, all the stochastic gradients will be zero as well? Yes, 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 that's fine. But do you agree that when you are in a minimum, you can pick any example that you want, but the stochastic gradient is also going to be zero, right? So that is important. Yeah.
One of the gradient sense is zero, but
Sorry, can you repeat the question?
like possible to have a point where one of the like one of the caves gradients would be zero, but we're not at
Yes, it's possible. Because the minimum is defined as sum of all the last functions, right? So it is possible. Any other question? Okay, so if you're in a convex setting, both these algorithms will converge, and they will converge to the global minimum. Okay, but when you are in a non-convex setting, this is when stochastic gradient descent is more useful, because gradient descent will always converge to the closest minimum, which could be local minimum. Stochastic gradient descent, because it is noisy, right? Sometimes it could skip the local minimum and move to the next minimum, which could be global minimum, right? So in non-convex cases, it's actually preferred to add stochasticity to your gradient descent, so that you're not always getting stuck in the closest minimum, okay? There are applications where it's just simply not possible to do full gradient descent. The best example is like streaming problems. So what are streaming problems? Like, so these are big data problems where the data is so huge, you cannot save it in your memory. So the data comes in, you learn from it, and throw away the data and move on. Okay, so extreme online learning. So which is different from the typical offline learning, which is what we have been focusing on so far. In offline learning, we would have a separate training data, separate validation data, separate test data, right? So in offline learning, we have a fixed data set. We are learning from the data set, right? But in online learning applications, there is no fixed data set. The data comes in and goes out. Every example, you need to make some prediction and learn from it and move on. Okay, so to give you a more realistic example, like let's say at CERN, right? Like, so when they are detecting events, right? Like, as something to be interesting or not interesting, it's a binary classification problem. Okay, but the data that the CERN collider generates is so huge, probably petabytes of data every second, that you cannot save all the data and do offline learning on it, okay? So you have to do online learning. So when you are in such extreme online learning situations, then SGD is the only solution. Is that clear? So typically, we will do SGD when you have a large data set that doing full gradient descent is computationally expensive, right? Or when you are in online learning settings. Is that clear? So when you do SGD, you're essentially going through all the examples one after another, right? So it is important that you shuffle the data set every time. Otherwise, what could happen is you got a bad ordering that every gradient is canceling each other and you're not making any progress, right? So let me write the SGD algorithm, like, to be more precise. So this is what we're going to do. We're going to initialize W0 and W1. and I'm going to repeat until convergence. Okay. First, I'm going to shuffle the data. So then, for I is equal to 1 to n, I'm going to do W0 is equal to W0 minus alpha times the gradient, which is y hat of xi given W minus y of I. W1 is equal to W1 minus alpha times the y hat minus yi times xi. Okay. So typically, this one round of going through all the examples to finish your stochastic gradient descent, right? So this is called an epoch of training, which means that when people say I did 10 epochs, it just means that they went through the data 10 times. Okay. You can also call it iteration. However, the word iteration is confusing because machine learning people use it in a different way than optimization people. So in optimization, one step is one iteration. But in machine learning, like sometimes when you go through the whole data set, that is an iteration. Okay. So if you see iteration, you should be careful. Depending on the context, it could have different words. Epoch typically means going through the data once from beginning to end. Is that clear? Yeah. That's another thing. Like say we go to the data. Yes. So the repeat until convergence is to go through this epoch multiple times. So within each epoch, you are actually going through each example individually and you're computing the gradient and doing gradient descent, right? So in a full batch gradient descent, there is no for loop here. The for loop is actually in the computation of the gradient, right? So you go through all the examples to make one step. But here, you're making one step per example. Is that clear? After you finish one epoch, you shuffle the data. Okay. So why do we shuffle the data? If you don't shuffle the data, you might have some bad ordering where the stochastic gradients just simply cancel each other. You're not reaching the minimum. So the shuffling is happening within the loop. So you will reach the minimum in the outside loop. Is that clear? So if I have to compare SGD and full batch gradient descent head to head, so the full batch gradient descent works like this. It's basically repeat until convergence. Okay. I'm going to initialize my gradient to be 0. For I is equal to 1 to n. So grad plus equal to dou loss I by dou w. Right? This is the for loop. Then w is equal to w minus alpha times the gradient. Okay. But SGD is going to be repeat until convergence for I is equal to 1 to n. W is equal to W minus alpha dou loss I by dou W. You see the difference between full gradient descent and stochastic gradient descent? Like in full batch gradient descent, I'm actually going through all the examples, sum all the gradients, and take just one step. W is equal to W minus alpha times grade, right? But in stochastic gradient descent, I'm going through every example, and for each example, I'm actually computing the gradient and taking the step. Is that clear? Any question? Okay, so these are two extremes. In one extreme, we have full batch gradient descent, which goes through all the examples and compute the gradient after that, like compute the step after that, right? And in the other extreme, we have stochastic gradient descent, which sees one example, computes the gradient, right? Now you can actually do something in between. Okay, so we have full batch gradient descent, stochastic gradient descent, right? So we could do something in between. It is called mini batch gradient descent. Okay, so with gradient, the full batch gradient descent, we were using all the n examples, right? With stochastic gradient descent, I was using just one example, right? So with mini batch gradient descent, like we would typically use some k examples, where k is much smaller than n. For example, 10 examples, 20 examples, right? This is going to be a little bit faster than SGD because SGD actually is taking one step per example, but then like these are all too many steps, right? So with mini batch gradient descent, like you're taking 10 examples, you're making a jump for each 10 example. Okay, so the benefit of mini batch gradient descent is the variance of the gradient is going to be a bit better. SGD is too noisy. Okay, so SGD is going to point you in all directions because you're doing it for every example, right? And when you add more examples, then you're better approximating the true gradient. So if your true gradient is with million examples, with 10 or 100 examples, like you're doing better approximation of that. Yeah. Yes. So okay. So the way in which you will implement this is, let's say you have 1,000 examples, and your batch size is 100. This means you're going to take your data, shuffle it, create 100 batches out of it, sorry, 10 batches out of it, so that when you go through all the 10 batches, you have covered the entire data, right? So even with mini batch gradient descent, you should make sure that you cover the entire data. But then you shuffle in the beginning so that you see different batches at different times. Yeah. No. Okay. So batching is just a way to aggregate things and take less noisier steps. Is that clear? And variance reduction is one useful nature of mini batch gradient descent, but the more practical application of mini batch gradient descent is that it is just simply GPU and TPU friendly. Okay, so which means you can actually train your models with GPUs or TPUs, okay, which is going to be much faster than training them using CPUs. Is that clear? Because when you do mini batch gradient descent, everything becomes matrix multiplication or matrix vector multiplication. Okay, which is what GPUs and TPUs are good at doing. Yeah, tensor processing unit. So it's similar to GPUs, but maybe more over optimized for matrix multiplication. Okay, so interesting fact is GPUs were invented not for machine learning, like primarily for games, like and graphics processing, right? Where the main application was games, but people did not realize 10 years back that like the most important application of GPUs, it's 125 is going to be machine learning. Okay, so NVIDIA's stock is so high right now because you need NVIDIA GPUs to train machine learning models, and machine learning is so successful, right? So it's probably one of the unexpected applications of a hardware, which the original inventors had no clue about, right? So anyway, so So then TPUs were invented specifically for machine learning. So when machine learning became so popular, when everything is matrix multiplication, right? Like so then Google invented TPUs, like so which were optimized for tensors, like and matrices or tensors. Okay. Okay. So GPUs and TPUs are good in doing matrix multiplications. Okay. And if you carefully observe the papers that are doing mini batch gradient descents, right? Like so, you would often see people using batch sizes of 64, 128, 256, etc. Instead of saying, oh, I'm using a batch size of 10 or 100. Can you guess why? So why is a batch size of 64 better than batch size of 60? So what's the benefit? Yeah. So the matrix multiplication is just faster with GPUs, like when your batch size is powers of 2. Okay, so it's just that there are faster algorithms. So you will actually see considerable difference in the computation speed by doing 64 versus 60. Okay. Okay. So I think so far we have seen 3 variants of gradient descent, right? So there is the original gradient descent, which is the full batch gradient descent, right? So then we have stochastic gradient descent, right? So then we have mini batch gradient descent. Okay. So typically when people say they use gradient descent in today's standards, it is almost always mini batch gradient descent. Okay. So nobody does full batch gradient descent because the data sets are so huge right now. I don't know if we ask you to do full batch or stochastic gradient descent in your assignment. So you should full gradient descent. Is it? No? Okay. We should check that. But for most of the practical applications, like the data is so huge that doing full batch gradient descent is not possible. Okay. So doing SGD is also not very efficient because you have a lot of data going through one by one is a bit slower, right? So typically when people say we use gradient descent, they are using mini batch gradient descent. Okay. Now mini batch gradient descent comes with 2 hyperparameters. What are they? Yeah. Batch size is a hyperparameter, right? Like, so what batch size you use is actually a hyperparameter. No. So there is a learning rate, right? So it still has the step size. So learning rate. So full gradient descent just has learning rate. Stochastic gradient descent also just has learning rate. Okay. Now, the versions of algorithms that I wrote in the slides says that repeat until convergence, right? But in practice, is it a good idea to repeat until convergence? Like, what is a good criteria to stop gradient descent? So the question is, when to stop gradient descent? Is it a good idea to repeat until convergence, first of all? Yeah? Okay. Let's say we reach it. Is it a good idea then? Yes. Okay. So you are both talking about the time it takes and whether we would reach the minimum, right? But my question is a bit different. Like, so in general, is it a good idea to run gradient descent until convergence? Like, so what could go wrong when you run gradient descent until convergence? Yeah.
You could overfit.
Yes, you could overfit, right? Like, because remember that you're doing gradient descent with respect to the training loss. So when you do gradient descent until convergence, well, of course, there is this question of whether can I converge or like whether it's going to take too long to converge, right? But in general, if you converge, there's also this chance that you are overfitting to the training set, right? Remember, our goal is not zero training error, but zero generalization error, right? So what would happen typically when you run gradient descent is you can track the loss, and in the x-axis, I'm going to put number of epochs. Okay, so each epoch is one iteration over the data. Let's say I do hundreds of epochs of gradient descent, right? So what would happen is typically the training loss will go down, right? Because you are fitting the training data, but the test loss, right, or the validation loss is going to go down for some time, and when you start overfitting, it's going to increase. Is that clear? So what people do in practice is track the validation loss. Okay, so whenever you get a minimum validation loss, note down that epoch number. Okay, so in this case, this is the place where you got the minimum validation, right? So which means this is the epoch that you should stop. Okay, but in practice, you would not know when to stop until the validation loss goes up, right? So in practice, what you would do is you would just store a checkpoint of the model parameters whenever the validation loss is lower. And when it starts increasing, then you know that, oh, now I'm overfitting. So I'm going to go back to the checkpoint of the model, like at this particular epoch. Is that clear? So this is a way of doing model selection with gradient descent. So every epoch, you're going to check for both training loss and validation loss. If the validation loss goes down, then you store the checkpoint of this model. Okay? If the validation loss keeps going down, you update your checkpoint with the current version of the model. But when the validation loss starts increasing, now you know that the model is overfitting. So you can go back and use the checkpoint from the previous validation loss. Yeah?
Is it possible to have a local minima and a validation loss?
That is a good question. So is it possible that it looks like the loss is going up, but then like you did not reach the global minimum? Is it possible? Any thoughts? It is possible sometimes, okay? So the curve looks too neat here, but this is not how the real curves would look like. So you might see ups and downs. So just because you have a small up doesn't mean that like you have reached your best thing, right? Like, so which is why you would see people running these algorithms for lots and lots of epochs. Okay, so you would run it for 1,000 epoch and see that whatever the best validation loss that you got in these 1,000 epoch is probably the best model. Is that clear? Now, sometimes it's not clear how long you should run, right? Like, so then people do what is called early stopping. Okay. So what early stopping means is you will set some patience number. Okay, let's say if I set my patience to be 5, this just means that, oh, I'm going to wait for 5 epochs. If I keep overfitting for 5 epochs, then I want to stop my training. Okay, depending on how patient you are, like you could increase the patient's number. Like so, like you could just say, I'm going to try to see for 100 epochs if the model is overfitting or not, right? So there are many heuristics on detecting overfitting and like finding the best parameter. Is it clear? Any question? Okay, so now there is another surprising benefit of doing gradient descent. Okay, so to explain that benefit, like I want to go back to the sine curve example. If you remember from the previous lecture, so we had a sine curve regression problem, right? Like, so I took some examples from a sine curve, data points from sine curve, and I was trying to fit a line, right? Then we went to do polynomial regression. So with polynomial regression, we found that when you have 10 data points and you're doing a polynomial of degree 10, it was overfitting, right? So now I'm going to repeat the same experiment, okay? I'm actually going to do 20-degree polynomial, but instead of doing closed form solution, I'm going to do gradient descent. Okay, I'm doing full gradient descent, like so I'm not doing stochastic gradient descent. I'm doing full gradient descent with a 20-degree polynomial on the sine function. Okay, so the surprising result is it doesn't overfit as much as a 20-degree polynomial closed form solution would overfit. In fact, you see here, this is actually doing a great job, right? Like so, for a 20-degree polynomial with no regularization, I'm not doing L2 regularization here. Okay, with just a simple 20-degree polynomial and full gradient descent, the curve looks very close to the sine curve. Well, of course, there are some overfitting happening in the corners, right? But this is very different from the solution. Well, maybe I should have plotted the solution for the closed form. So the closed form solution is going to look something. Well, maybe this is not accurate, but you get the idea, right? Like the closed form solution is going to look perfectly overfitting the examples, but completely different from the sine curve, right? So why is this happening? Shouldn't we get the same solution, like irrespective of whether I'm doing gradient descent or I'm trying to minimize least square, right? There are two ways to minimize least square. Like one is the x transpose x transpose y rule. The other is to do gradient descent. Shouldn't I get the same solution like for both? Like, so why is this mismatch happening? Yeah. We are doing least squares. There is only one minimum, right? So this is convex function. By the way, this is a very interesting effect of gradient descent. Okay, so even though gradient descent exists for many decades, like so, this effect was well documented only in 2015, 2016. So it's any thoughts like why this should happen?
For the gradient descent go in and the error requirement. So yeah, also really give the point back.
Yes. Yes.
The full sum is longer accurate. Therefore, it needs a longer read.
No. Oh, no. Think about how gradient descent works. Yeah. Okay. Different parameter initialization. Okay, any other thoughts? Any other thoughts? Okay, so with gradient descent, we typically initialize the weights to a very small value, right? So we are already initializing the weights to a small value. And the nature of gradient descent is to just find the closest solution. In this example, when you have 10 data points and 20-degree polynomial, there are infinitely many possible solutions. Okay, and gradient descent actually has this implicit bias to find low norm solutions. Or in other words, it's actually implicitly using L2 regularization. Because the nature of gradient descent is always to go to something closest and smallest. Okay, so this is what people call as implicit regularization of gradient descent. Okay, so it has this implicit regularization behavior because we initialize it to small value and we are trying to reach the closest minimum. Okay. However, this is actually super useful in this simple example, but as models get more and more complex, this implicit regularization is not enough. We need to have explicit regularization like L2 regularization or L1 regularization. We are going to discuss a few regularization techniques after the break. So we need explicit regularization. Okay, so this is just to show that there's already something nice happening with gradient descent. And remember that this is full batch gradient descent. This is true for full batch gradient descent, mini batch gradient descent, or even stochastic gradient descent. Is that clear? Yeah.
What do you mean by implicit bias?
Well, there's an implicit bias to find low norm solutions. Okay, so if I go back to the same exercise we did last time, like where I just simply vary the degree of polynomial and plot the train test errors, right? So if you remember the curve from last week, there was massive overfitting happening, right? So here you actually see that I'm doing 3, 3, 4, 5, 6, 7 all the way to 8. There is no overfitting happening. Okay, with gradient descent, like I'm actually able to find a good solution, which means gradient descent actually learns to suppress some of the degrees and give the solution, the optimal solution that we need. Is that clear? So, which is further confirmed here. Like so, here you see the weights after learning with gradient descent. So with the closed form solution, like we saw that these weights were exploding, right? Like very large values. But with gradient descent, the weights are still manageable. Somehow the gradient descent is actually nicely using all the 10 parameters in a way that it fits a reasonable sine curve. Is that clear? Any question? So I have added a paper on implicit regularization of gradient descent as an optional reading, but it is highly mathematical. So you don't need to read it if you're not interested in math, but you can at least skim it to get an idea of the nature of this property. Is that clear? Any question? Okay, so let's take a break. So then we are going to talk about regularization.